Thank you all. Yes, this is Fiat Lux IV. The Fiat Lux trilogy moves on. And this is episode 4, Colour in the Cosmos. So roughly speaking, I'm going to do a short introduction and then have a look, before we talk about colour that's out there in the cosmos, we're going to have a think about colour a little bit closer to home, the way humans perceive colour, and how we quantify colour. Rather than try and give a name to every conceivable colour, how do we try to quantify it? Then I'll be moving into the cosmos and thinking about the colour of stars and the colour of nebulae and why they are different. If they're made of the same stuff, nebulae and stars, why are their spectra, why are their colours so different? And then I'll be having a brief look at other aspects of spectroscopy, splitting light into its component colours, and finishing off with just a few thoughts about false colour imaging, and then a little summary at the end. So we can start with what is colour, because philosophers will debate this almost ad infinitum. Is colour real? Is colour out there? Or is colour just something in our heads? In other words, is it real? Or is it just a pigment of your imagination? Well, thank you. There's more like that to come. So we can start with the question, why do humans have colour vision? Why do we see colours at all? Well, of course, rainbows would be pretty damn boring if we didn't have colour vision, but we can still ask ourselves, what was the driving force to give us colour vision? Some people disagree, but a lot of people seem to think the main idea behind colour vision is so that we can tell when fruit is ripe. If we're swinging around in the trees, as we were a little while ago, we have to decide, is it worth my while getting out of this tree and going to that tree because the fruit over there looks like it might be ripe? If you've got colour vision, you can tell before you make the journey. You don't have to go and then find the fruit is not ripe yet. So here's 3 fruits. Which of them are ripe and which of them aren't? Any guesses? Nobody wants to guess. Without colour vision, difficult to tell. With colour vision, absolutely obvious which ones are ripe and which ones aren't. So you can see this even from a great distance. Personally, I think it's nothing to do with fruit. I think the reason we've developed colour vision is because otherwise maps of the London Underground would be impossible to make sense of. Look at that spaghetti. Without colour vision, you can't see what's going on. With colour vision, you can actually get from A to B. So that, I think, is an evolutionary driver in its own right. So how do we perceive colour? This is something I'm sure you know, but I'll cover it again anyway. The human eye is a little orb in which light enters through the cornea, and the lens is focused onto the retina, and we see because the retina is covered with a whole load of photoreceptors. So we can think of those photoreceptors as being, some of them respond to red, some to green, some to blue, and the retina is actually packed with them. Millions, if not hundreds of millions, of photoreceptors on the back of the eye. Those photoreceptors take the light that's come through the cornea, through the lens, they convert the light into an electrical signal, and that electrical signal is fed to the brain. Okay, that all seems fair enough. So the knee-jerk reaction is to say, well, if we capture light with a lens and then we pick up the light and then we convert it to an electrical signal, isn't that exactly what a digital camera does? A digital camera takes light through the lens and then it focuses the lens onto a chip, and if we look at what's going on that chip, we find a whole load of photoreceptors, and the usual cheat to get the colour reception on a particular digital image is to use a so-called Bayer grid. This is simply a grid of filters, some of which are red, some green, and some blue. And hence, we can read out electronically the amount of light arriving at each pixel in the chip, and then decode that as we've got this much red, this much green, this much blue, so we know what the colour of the light was. Now, the filters themselves let through a certain amount of light in the visible spectrum, and this is one particular camera. Other cameras will differ slightly, but this is a particular camera, and we can see how much light the blue filter lets through, and the green filter, and the red filter, and we can see that we cover most of the visible spectrum. It's not very efficient. Cameras aren't very efficient at the extremes, but then neither are our eyes, so that's not altogether surprising. But you can see that there's a fair overlap between the colour reception of the red and the green and the blue pixels in a digital camera. And we might say, well, that's pretty much what the eye does as well. The eye has red, green, blue receptors. It's biological rather than semiconductor, but presumably it looks pretty much the same. Well, actually, if you look at the response of the human eye, it looks rather different. We have a relatively narrow band in the blue, and look at the red and the green. The red and the green are not the same, but they are very close. And we can ask ourselves, why might that be? Surely that's a little bit redundant to have red and green so close to each other. But actually, having two responses that look like that actually enable us to distinguish red and green quite effectively, because these two are actually quite close together. The other thing we might notice is that, remember the spectrum, which I'll often show at the top of these graphs to remind us where we are in terms of the visible spectrum. The spectrum doesn't go from red to blue. We all know the mnemonic: red, orange, yellow, green, blue, indigo, violet. It doesn't end at blue, it goes slightly red at the end. The blue end of the spectrum is actually tinged with red. Why do we see short wavelengths tinged with red when we know that red is at the long wavelength end of the spectrum? Well, look at red. It doesn't actually peak at red. It actually peaks in the middle of the spectrum. The red photoreceptors in our eyes actually respond to all colors from 700 all the way down to 400 nanometers. Notice that it's still quite finite. There's a fair bit of reception even at this end. So the very shortest wavelengths will actually make the blue receptors respond, but actually the red receptors will also be responding slightly. And that's why we see the blue end of the spectrum as violet rather than simply as blue. So human vision isn't quite what you think it is. And indeed, biologists, of course, have known this for quite a while, and they do not label these three sets of photoreceptors, red, green, and blue. I'll continue to use those labels from now on, but biologists actually refer to these three photoreceptors as the long wavelength and the short wavelength and the middle wavelength receptors, because they do not measure just red, just green, and just blue light. And it's a reminder that human vision is not quite as simple as we thought it was. Just to complete the picture, this is nothing to do with color per se, but just to remind us that as well as having three photoreceptors for color in our eyes, red, green, and blue, we also have a whole set of rods. Let me get rid of the colors. The rods are receptive to low levels of light, but we have no color sensitivity. So our night vision is based on a different set of cells. We can't distinguish colors at night, but we can see low levels of light. And if you notice where the reception, the light sensitivity of the rods are, we're sensitive to blue and green, but the rods tell us nothing about red light, which is why astronomers use red lights at night, because it does not affect the rods and it does not affect your night vision. So you can see quite happily in red light at night, and when you switch the red light off, your rods, which are sensitive to low levels of illumination, have not been affected by the fact that you've just switched a red light on. That's why we use red rather than any other color to protect our night vision. So we might say to ourselves, okay, we have rods, which are low light receptors, and we have red, green, blue photoreceptors in our eyes. But some animals have somewhat different eyes to us. So we know that we have what we call trichromatic vision, in other words, vision in three colors, but some animals are quite different. For instance, there's an animal, and again, the colors up here tell you that this is the visible part of the spectrum. Some animals have got more than 12 different types of photoreceptor in their eyes, one of which is actually sensitive into the infrared. The other photoreceptors cover the entire visible spectrum, and some of those photoreceptors actually go into the ultraviolet. Anybody care to guess which animal this was taken from? It's actually this little fella, the mantis shrimp. Why a mantis shrimp needs 12 sets of photoreceptors, and what the hell does its little brain do with all of this information, I don't quite know. There must be some evolutionary drive for that little colorful fellow to actually have developed 12 different color receptors. So we don't need to worry about what its names are for all of those colors, because even if we could ask it, it obviously wouldn't reply in any language we could understand. But we can ask the question, why did we end up with 3? We've ended up with 3 color receptors. We call them red, green, and blue, but of course that's just arbitrary labels for what these 3 color receptors actually give us. Why did we end up with 3? Well, if you go back far enough in history, many, many hundreds of millions of years, we had color vision, and then we lost it. And we lost it around the time of the dinosaurs. When the dinosaurs ruled the Earth, we were nocturnal, or at least our ancestors were nocturnal. And so we went out at night, because if we went out during the day, we got stomped on by dinosaurs. So we stayed in during the day and only hunted at night. So at night, we needed good night vision, but we didn't really need color vision. So we lost color vision when we were nocturnal 100 or so million years ago. Since then, of course, we've been evolving. The dinosaurs got moved to one side because of the asteroid that hit the Earth. And since then, we have undergone various genetic mutations, and our color vision effectively has come back. When we were swinging through the trees in the middle of this diagram, that's when we absolutely needed our color vision so that we could tell whether fruit was ripe or there were any other dangers around us. I'm not claiming that this is the end of the evolutionary line, as it were. I'm not claiming that trichromatic vision is the pinnacle of evolution. Man has not finished evolving yet. Who knows where evolution will take us next? It's very difficult to say what the next step of the evolutionary chain might be. But we have evolved to see invisible light, because visible light is one of the few parts of the electromagnetic spectrum that actually make it to the ground. Regardless of what radiation is hitting our atmosphere, visible light, this is a graph of transmission, so we can see that not much of the ultraviolet is actually transmitted, but there's a sort of window, if you like, in the visible part of the spectrum, which means most, about 95% or so, of visible light that hits the top of the atmosphere actually makes it to either ground level or the tops of the clouds, depending on the weather. You can see there's another window in the radio, but as far as I know, no animals have ever developed the ability to see in radio, even though there's lots of it arriving, mainly because the wavelengths are meters or tens of meters. And basically, you can't see wavelengths that are 10 times bigger than you are, so no animal has developed that ability. Light makes it to the ground, so of course, if we build telescopes on the ground, we can see the universe, because essentially very little of that light is absorbed. But all of the ultraviolet and most of the infrared are absorbed, so if we want to see the universe in the UV and the IR, we basically have to put up satellites or telescopes into orbit, such as the various ones that have been put up in the UV on the left there, and in the infrared, James Webb, Spitzer, Herschel, etc., on the other side there. Of course, we don't need to put a telescope that works in the optical above the atmosphere, because we can see perfectly well down here. In terms of transparency, that's not a problem, but of course the atmosphere is actually turbulent, and hence there is an advantage to putting a space telescope such as the Hubble up in orbit, because that gets us above the atmosphere. It's nothing to do with how much the atmosphere absorbs, it's entirely the turbulence of the atmosphere. So we have evolved, our eyes have evolved to give us sensitive discrimination within that narrow band indicated by the rainbow there, just a little bit less, wavelengths a little bit less than 1 micron. And the way our eyes have done that, or the way that evolution has pushed the development of our eyes, is quite interesting, but it's not quite as simple as my earlier cartoon would imply. There are sensors for red, green, blue in the retina, and they send signals to the brain. It isn't actually that simple. What's going on in the retina is these photoreceptors are there, but they only form one layer of what's actually going on in our retinas. There's a whole load of other cells that are attached to those photoreceptors. These are neurons. Yes, your brain is full of neurons. That's what allows you to think. But your eyes are full of neurons as well. There's a whole load of cells whose job it is to take signals from the photoreceptors. These neurons do some image processing. They take the signals from the photoreceptors, and they do various things to those signals before that gets passed on to the brain. So it's like having, if you like, mini brains inside your eyes doing some of the work to take the load off the brain itself. And we can sort of, in a cartoony way, think about how that actually works. If we again draw an analogy with a digital camera records the amount of light arriving on the chip having passed through 3 red, green, blue types of filter. So we get red and green and blue intensities. We get a record of the intensity of red, the intensity of green, the intensity of blue. And that information is passed almost directly on to the output, which is make an image and stick it on the SD card of the camera. In other words, the red and the green and the blue of the image you end up with is effectively the same as the red and the green and the blue as recorded by the chip. Not quite, but close enough for our purposes. There's probably a little bit of juggling of the actual values of intensities as recorded, but there's a one-to-one map between what's recorded by the chip and the image you end up with. That's what the camera circuitry does. The eye is very different because of these neurons that are attached to all of your photoreceptors. So you've got, if you like, red, green, blue recorded by the photoreceptors of the eye, but the first thing that happens is the neurons that are connected to those photoreceptors start processing that information. In other words, one particular neuron, these gray circles represent the neuron cells that are in the back of your eye. They won't necessarily record how much green light has arrived or how much blue light has arrived. They might record how much light overall has arrived. Or they might be recording, well, what's the difference between how much green and how much blue? And that information is then passed on to the next set of neurons, which eventually pass it on to your brain to try and work out what it is you're looking at. So it is far removed from the idea that whatever the chip sees, that's the image you get. The eye doesn't work that way. And I can prove that by showing you a particular interesting image. If any of you are colorblind, I'm afraid this is not going to work too well. On the left-hand side, you see a cube with lots of colored tiles on it, yes? We're only interested in the top face. Forget the face that's facing you and on the right-hand side. We're just interested in these 25 tiles here. On the left-hand side, over here, how many of those tiles on the top face are blue? Most of you thought 4. Does anybody want to disagree with that? 27, wrong. Okay, so you think there were 4 blue on the left. Okay, now cast your gaze to this cube on the right. Again, only looking at the 25 tiles on the top face of the cube, how many of them are yellow? So most of you seem to think there were 4 blue tiles on the left and 7 yellow tiles on the right. Are you prepared to put money on that?
Not with you, Steve.
Yeah. You may be interested to know that the 4 blue tiles on the left and the 7 yellow tiles on the right are actually the same color. Yes, you heard me correctly. The 4 blues on the left and the 7 yellows on the right are actually the same color. And I can show you by removing all of the confusion. And the confusion is all of the colors that surround those particular tiles. So I'm going to take away all the pixels except for the pixels in those 11 tiles. And if I do that one step at a time, that is what you are actually looking at without all the extraneous pixels in the background. They're not blue on the left. They are not yellow on the right. They are all gray. Let me put the other pixels back again, and if I put the other pixels back again, your brain is now telling you they're not gray, they're blue on the left and yellow on the right. But they're not. Your brain is lying to you. It's the neurons in the back of your eye taking the information from the photoreceptors. They are not telling you this is the amount of red, green, and blue. It's telling you this appears to be redder than that. This appears to have more green in it than that. It's doing lots of comparisons, and your brain is ending up telling you things that it thinks you need to know, as opposed to absolute light levels, which is what a camera ought to give you. So point number one is you cannot believe the color vision of your eyes. You can sometimes say, yeah, it's a nice blue sky today, but when you're trying to compare two colors, you can be fooled, and you can be fooled relatively easily. And just to convince you that your eye is doing a lot of processing, not necessarily involved with colors, let me just go back. There's the original, the actual tiles themselves. Let me just give you a brief aside, because this is nothing per se about color vision, but it is pertinent in that it tells you the processing that your eyes are doing. Here's another interesting anomaly, as it were. There's a square labeled A and a square labeled B. It's not the letters I'm interested in, it's the squares on which those letters sit. Which is the darker of the two, A or B? Sure? Okay. Let me do something similar to before. Let me block out the confusing pixels on the left and the confusing pixels on the right. And I'm literally just going to mask them off, one at a time. Okay? So if you look at the gray of A, and you look at the gray of B, and you look at the gray of the next one down, they're not similar, they are identical.
A is still darker to me.
A is still darker. Do you think that that grey is the same as this grey?
No, it's slightly darker.
It is exactly the same. Those two greys are exactly the same, and those two greys are exactly the same. There's no line here that shows you a difference in the density of the grey. So having established that A and B are exactly the same, and I've checked this by actually taking a computer and actually recording the pixel values, they are exactly the same. So if I take those masks away, you know that those two tiles are the same shade of grey. You know there's the same amount of light coming from square labeled A and square labeled B. But it's impossible to override your brain and to say, well, I can see it, that they're actually the same. Your brain is screaming at you that square A is actually darker than square B. But that's purely because your brain is effectively processing information, and your eyes are processing information from neighboring pixels, if you like, from neighboring regions, and telling you about the difference between this square and the neighboring square, or this square and the neighboring square. So even though they are actually sending you the same amount of light, you don't see it that way. So variable star observers, beware. When you're looking at two stars and you think one looks brighter than the other, are you absolutely sure? If you have a camera and you record it, you can be sure. If you're looking at two stars, there will always be that doubt. Are you actually correctly assuming that that star is brighter than that star? So perception and reality are two very different things. So how can we quantify color? I better get a move on or I'll be here all night. So if we want to quantify color, we could say, well, we quantify it with a spectrum, not that sort of spectrum, a different sort of spectrum, the one our friend Isaac Newton came up with when he was trying to reproduce the front cover of the Pink Floyd album. So in the 1660s, he showed that white light can be split, and now we can look at a spectrum and say, okay, depending on where this particular color is on the spectrum, we can quantify it from one end to the other and measure where colors occur in the spectrum. So we know from Newton's work and from many other people's work in centuries past that light is an electromagnetic wave, and if we take that wave and we measure the wavelength, the distance from one crest to the next crest, we find that visible light falls into this range. The red end of the spectrum is at 700 nanometers, or 0.7 microns, and the violet end is at 400 nanometers. So essentially anything between 400 and 700 nanometers in wavelength is what we perceive as visible light. Slight variation amongst different humans. But that's not all there is to color, because not all colors are spectral colors. Not all colors occur in the rainbow. For instance, where's beige in the rainbow? Where's brown? They're not there. The colors of the rainbow are just a particular subset of colors. To show all colors, we need more than just that. And 100 or so years ago, it was decided by a group of people, the CIE, that's their name up the top there. They decided that one way of representing colors is not to have a line of colors, but to have a two-dimensional space, a so-called color space. We're not going to worry about what the axes mean, and we're not going to worry about why it's an odd-looking shape, but we are going to think about colours that can exist in that particular space. And if we think of spectral colours, they exist on the outside of that particular loop. In other words, all colours that occur in the spectrum occur at the edge of this particular way of representing all colours. Notice they're not equally spaced. Red are quite bunched up at this end, blue quite bunched up at that end, green appears to be quite spread out. That's a function of this particular colour space mapping reasonably well to human perception of colour, where we have the ability to separate shades of green quite well. We are less able to separate close shades of red or close shades of blue. That's the way our photoreceptors work. But there is a problem with the technology. I'm looking at a laptop screen, you're looking at the output from a projector, but these are both digital devices. And any digital device, whether it be a phone, an iPad, a TV, a data projector, or whatever, they will only be able to represent a certain subset of colours. In this particular case, it might be that the red and the green and the blue of this projector are indicated by the tips of this triangle, and therefore we cannot represent any colours outside that triangle. So you can think of the primary colours red, green and blue existing in this space, and if you mix red, green and blue, you can generate any colour you like inside that triangle, but you can't generate colours outside the triangle. That's why all of these colours look the same. That's why all of these greens look effectively the same. We can't distinguish them because this projector and my laptop and various other devices are incapable of separating, distinguishing, discriminating between all possible colours. Only a subset, a so-called gamut, are actually distinguishable on any TV or monitor or display that you might have. So that's something to bear in mind, and that's why an image that you see on this device doesn't necessarily look the same when you show that same image on another device. They don't necessarily have the same set of colours, and so the image doesn't necessarily look the same. So we've thought about colours, and I hope I've convinced you that colours are not quite as simple as you might first have thought. So let's think about the colours of stars. Where do colours of stars fit on this picture? If we were to take lots of stars in the sky and plot them in terms of their colour, would you expect stars to be peppered all over this particular colour space? Turns out no. The colours of stars must obey the laws of physics, and when you think about how objects behave, if you take an object and heat it up, it doesn't really matter whether that object is a lump of steel or whether that object is a star. The radiation they produce, the light they produce, has to follow a certain set of rules, which we call quantum theory, which we're not going to cover in detail. But when we actually plot out where are all possible stars, it's actually much more restrictive than you first realize. The total possibility for stars is only those on the line, on that curve. Coolish stars on the right, hot stars on the left. Coolish red stars at this end, hot white or slightly bluey white stars at the other end. We don't get purple stars. We don't get green stars. We only get stars that fall on that particular range of possible colours. And I'll show you why that is. If you take an object and heat it up, in this case a piece of steel has been heated from the right-hand end and it's got white hot at this end, and the temperature has decreased as we go along. And you can see the cold end seems to be either black or actually it's radiating infrared light, and when it's red hot it looks mainly red, and if it's hotter than red hot it looks a little bit orange, and if it's really hot it's white. So the colours change as we heat up an object. And this particular little diagram, I know there's a lot going on in here, but I borrowed this from the physics education resource, PhET, as it's a very nice little applet that shows what's going on. Here we're plotting how much light is emitted by an object at a given temperature. So the word black body sounds a little confusing at first because clearly things are glowing. But black body means we're starting with an object that doesn't reflect any light from its ambient surroundings. We're talking about an object, if you painted it black, we're talking about an object glowing because it's hot, not producing colour because it's reflecting any light around it. If you take an object and heat it up to 1200 Kelvin, this is the light that it will emit. This is how much light is given off as a function of the wavelength of light, in this case plotted from 0 to 3 microns. And as a reminder, ultraviolet light is on the left-hand part of the diagram, visible light is indicated by where the rainbow is sitting, and infrared light is everything to the right of the red. So if we have an object at 1200 Kelvin, that's the sort of light that it produces. A lot of infrared and essentially no visible light. If we were to take an object and warm it up, for instance, if we went up from 1200, note that the peak at the moment is sitting about here. Two things happen if we take the temperature up. The peak gets higher, in other words, there's more light emitted. When you heat something up, it gets brighter. But more importantly for us is the peak where this occurs starts to shift towards the blue end of the spectrum. It's still in the infrared here. At 1500 Kelvin, we're still emitting a lot of infrared and essentially very little visible light. From now on, I'm just going to make sure they're all plotted on the same scale. Even though more and more light is being generated, I'm just going to keep that fixed scale. But if we go up from 1500 to 2000 Kelvin, we are now pushing towards the visible part of the spectrum. It's still effectively just a rather warm or rather hot object, but you can see now that we're starting to just emit some visible light. Most of the light is still in the infrared, most of the radiation is still in the infrared, but we're now starting to produce a little bit of red, a tiny amount of blue. And if we get to the point where we have the surface temperature of a red giant, somewhere about 3000 Kelvin, most of the light from a red giant, again, is actually being radiated, not in the red, but in the infrared. But clearly, that's starting to now drift into the visible part of the spectrum. And so the light output of a red giant, there'll be a lot of red and very little blue, which is why a red giant looks red. Not because all the light it emits is red, but simply because there's much more red than there is blue, and so the star appears red. If we push the temperature up to the temperature of the sun, now the brightest part of the whole curve is now in the visible. We're no longer emitting most of the radiation in the infrared. We're now emitting a lot of the radiation in the visible part of the spectrum. Some in the ultraviolet, some in the infrared, but quite a lot in the visible. Notice that we are now radiating in the red and the blue and effectively all the colors of the rainbow. They're not quite the same height, but they're almost the same height. All the colors of the rainbow, red, orange, yellow, green, blue, indigo, violet, all colors are radiating from the sun, which is why the sun looks essentially whitish. Maybe a tinge of yellow, depends on whether you're close to sunset or not. If we were to push the temperature even higher, beyond the temperature of the sun, for instance, a star like Vega, then we've pushed the maximum of its output all the way to the left. It's now radiating most of its light in the ultraviolet. And of course, if with most of the light is in the ultraviolet, very little in the infrared here, we can see that a lot of light is irradiated, a lot of blue light is produced, a little bit of red light. So if this star is generating a lot of blue and a little bit of red, it's going to look bluish. And that's why we have, if I go back to red giants emit mainly red, very little blue, so they look red. Stars that emit in the visible spectrum emit essentially all colors, so they look whitish. And if we get even hotter, stars emit in the ultraviolet, which means they emit more blue than red. So stars are either reddish or whitish or bluish. No purples, no greens, no other combinations of colors. The laws of physics dictate what that curve has to look like. Quantum theory tells us we must have that curve. And we can't ever end up with a star which emits, for instance, in the middle of the spectrum, but nowhere else. No ultraviolet, no infrared, no red, no blue, just green. You cannot generate a star to do that. It disobeys the laws of physics. So when we plot stars, if we take all the stars that we can see, essentially any star we could measure in the galaxy, we could, if we wish, plot it on a graph of temperature running sideways, and for historical reasons, it's cold on the right and hot on the left, so the scale looks backwards, as it were. And the vertical scale is luminosity. How bright is that star? And for convenience, we simply label it with the brightness compared to the brightness of our sun. You can see the scale down here. It's only schematic, showing you essentially what the color looks like. All it's there for really is to remind us that it's red on the right and blue on the left. And if we took a piece of steel, remember there's an approximate combination of, the colder ones are red and the hotter end of the bar is white. So the sun is in the middle there. The sun is emitting, it's a luminosity of 1 because it's the luminosity relative to the sun's luminosity. The surface temperature is about 6,000, so whether you say it's slightly yellowish or slightly whitish, it doesn't really matter. The point is it's not particularly red and it's not particularly blue. But these so-called either color magnitude diagrams or luminosity surface temperature diagrams are very useful because it can not only tell us about, yes, we can classify stars by seeing where they appear on a diagram of color this way and luminosity that way, we can actually understand something about how stars work based on these diagrams. For instance, it turns out that the large stars end up in the top right-hand part of the Hertzsprung-Russell diagram, and small stars, small radii stars, end up in the bottom left part of the diagram. Not only that, but really big, massive stars end up in the top left part of the diagram, and small mass stars end up in the bottom right. We can talk about stellar evolution, but of course that's a different talk as to why it ends up that way. But because we know that relationship, we can now look at a star cluster, for instance, and say, if I were to photograph that star cluster, either as an amateur, or if the Hubble Space Telescope was asked to do this, you can take a picture of a cluster. Most of these stars are at the same distance. So if you take a picture, you clearly get some color differences. Some of these stars look rather red, some of them look rather blue, some of them look a little bit white. You can ask a computer, after you've taken this picture, to go through and measure the brightness of every star and the color of every star. In other words, for the 10,000 stars that you've got in this image, you can say what is its brightness and what is its color. And hence you can plot it on a Hertzsprung-Russell diagram. And indeed, we've asked some of our undergraduate students to do precisely this. Take a picture of a cluster and work out where they would fit on an HR diagram. The vertical axis of a Hertzsprung-Russell diagram should be the luminosity of the star, and we don't know how luminous that star is. But all of these stars are at the same distance, so we don't actually need the luminosity. We just assume if they're all the same distance, then if this star looks brighter than that one, let's assume that it is brighter than that one because they're all at the same distance in the sky. So we can plot every star in a cluster on an HR diagram. And for simplicity, I'm going to ignore some of the stars. Most of the stars will end up on the main sequence, on this diagonal line from top left to bottom right. There will be a whole load of other stars in this top right corner. There will be a whole load of other stars in the bottom left corner, but I'm just going to ignore those for the time being, for simplicity. The top left are the really big blue supergiant stars. These are the ones that are burning their fuel really fast to maintain the radiation pressure to support a massive star. The ones in the bottom right are red dwarfs. They don't have much mass. They don't have to burn their fuel very fast. So they are very long-lived. And effectively, there's a timeline along an implicit timeline that we can calculate along the main sequence. So what that means is, if we find that this set of stars that we plotted in the cluster goes all the way up to the top left, that means none of these really big blue stars have died yet, because they're there. If we see them all the way up to the top left, the really big, short-lived stars are still there, so the cluster must be young. And similarly, if we see stars but only as far as there, for instance, we can calculate, well, some of the really big blue stars have died, so this cluster must be quite a few million years old, maybe 20 million. And similarly, if we only get as far as there, this cluster must be 100 million years old, or 1 billion years old. Here, the arrow is pointing roughly where the sun is. And we know the lifetime of our sun is about 10 billion years. We're about halfway through. It's 5 billion years old, another 5 billion years to come. So if we know that stars like our sun last for 10 billion years, and if we find that when we plot all the stars in our cluster, we find no stars that are bluer than our sun. They're all missing. That means the cluster must be about 10 billion years old. It's a statistical result. We can't be absolutely sure, but based on our understanding of how stars evolve, we can pin down with reasonable errors how old that cluster must be if all the stars are present up to this point, but none of them are present from that point onwards. So by plotting stars in an HR diagram, you can get the age of stars. Even if you don't know how far away that cluster is, you can still get the age of the cluster. And that is being done by the Hubble Space Telescope for trying to work out how old globular clusters are, for instance, and also open clusters. And as I say, we get our students to do this on images taken from smaller telescopes. They can't get as many stars, the results aren't as good, but the same principle still applies. And when we think about the Hertzsprung-Russell diagram, we could, if we wish, classify these various surface temperatures and put labels on them. It looks a bit of an odd mix of labels, O, B, A, F, G. It used to be, a long time ago, alphabetical order. And then they realized, we seem to have got A and B the wrong way round, and they made a few adjustments, and we ended up with that rather awkward set of letters there. And if we take the spectra of those stars, there's the stellar types, OBA, FG, KM, etc. They correspond to different surface temperatures. All of these stars emit across all of the spectrum, but the M stars, the cool stars, emit mainly in the red. The hot stars emit mainly in the blue and less in the red. As a slight aside, if I've got time for a slight aside, you could ask, what's the average color of all the stars? Some are blue, some are red, some are whitish. What's the average of all of them, all the stars in all the galaxies? Well, some astronomers with far too much time on their hands decided that they would try that, and they took the analysis of 200,000 galaxies within a couple of billion light years to calculate what the color of the universe is. And they found it's beige. The universe is beige. They needed a slightly better name than that, so they thought, oh, okay, what can we call it? Let's call it cosmic latte. Or my favorite is actually skyvery. I think that's quite a nice description. So we need to get a move on. We've looked at the colors of stars. What about the color of nebulae? Well, we've said that stars tend to be, well, they emit in all colors. Some of them will emit more in the red than the blue, and some vice versa, but galaxies are a mix of lots of stars, and so galaxies will emit across the entire spectrum. But when we look at nebula within our galaxy, we find that they only emit in certain colors. And the elephant in the room is, why? Because nebula are clouds of stuff that are yet to condense into a star, or they are stars that have blown themselves apart. So they're actually made of the same stuff. If they're made of the same stuff, why don't they look the same when we look at their colors? I'll come back to that shortly. But first, a little digression and a reminder that everything is made of atoms. Atoms have positive nuclei and negatively charged electrons buzzing around them. And the best way of thinking of them is in terms of sort of a little bit like a solar system. Physicists don't like that analogy, but that will do for the moment. The electrons are going around the nucleus like planets going around the sun, but the important thing is that different electrons have different energies because they are in different shells. That's a two-dimensional picture. There's a more three-dimensional picture of what the electrons are doing. If an electron is in a high energy level or a high energy shell, if it were to drop to a low energy level, this is just a hypothetical atom, if an electron loses energy, then it gives off that energy as a photon of light, a packet of light. And similarly, if an electron is in a low energy state and it absorbs a photon, if a photon comes in, that electron can jump from one energy level to another. The bottom line is, because every atom has a particular set of energy levels, then the energy levels of the atom are linked to the energies of any light being absorbed or light being emitted. And again, I'm not going to go through the details, but quantum theory tells us that every color has a particular wavelength and has a particular energy. And therefore, if an atom has a particular set of energy levels, we would expect it to emit or absorb light of particular colors. And that's why we get an emission spectrum. So any particular atom has a particular pattern, if you like, a particular arrangement of electrons around it, and that's why you get a particular set of colors because of electrons jumping between different energy levels, regardless of whether it's light being emitted or light being absorbed. So if we were to look at the colors of light emitted from atoms or light absorbed by atoms, we can tell which atom it is because we simply look at which colors are present, and that tells us from our understanding of quantum theory which atoms are there. For instance, if a nebula is made up partly of oxygen, we would expect to find a particular emission at this particular wavelength, 500 nanometers. If a nebula contains hydrogen, well, it just so happens that hydrogen will emit two fairly strong lines in the visible spectrum, one in the red and one in the blue. And if we were to look at a nebula that contains both, for instance, the Veil Nebula, let's just look at the eastern Veil there. It contains red and blue, and the emission we're getting from the hydrogen and oxygen in the Veil Nebula are at these particular positions indicated by the arrows, which means if we were to look at the red part of the image, we find that we're getting hydrogen because hydrogen is emitted at the red end of the spectrum. Green and blue are not very good at separating oxygen from H beta. They just happen to be. One thing I forgot to mention is if we look at that, H beta is a particular color from hydrogen, but notice that the number 486 is not so different from the oxygen at 500. They're actually quite close together, even though they look quite a long way apart in that diagram. They actually are relatively close together in terms of their wavelength. So we can see differences when we look at the red and the green and the blue part of a color image, and we can see where the hydrogen is and where the oxygen is, but this is not the ideal way of doing this sort of experiment. Ideally, we would pick only the emission from hydrogen and only the emission from oxygen to get the best possible picture of a particular structure. So returning to this idea of the elephant in the room, light from a nebula is based on atoms have particular energy levels. Jumping between those energy levels gives you particular colors, such as the red of hydrogen, the blue of hydrogen, the cyan color of oxygen, for instance. So we can identify which atoms are emitting this light. But when we're talking about stars, we said, well, if you heat something up, you get a particular spectrum, and it doesn't really matter what you're heating up, whether it's a lump of iron or whether it's a star. So if these things are made of the same things, hydrogen, helium, oxygen, a bit of other elements, why the fundamental difference? Well, the difference is in the density of what we're looking at. It's how many atoms we have in a particular volume. In other words, if the atoms are well separated from each other, we would expect each of the atoms to emit the colors that we were talking about according to the laws of quantum theory. But if all the atoms are close together and bumping into each other all the time, then effectively these so-called discrete spectra get smeared out into a continuous spectra, and hence we get all the colors of the rainbow. So what matters is, are the atoms well separated or are the atoms close together? And so we can think about how many atoms we have in a particular volume, and that will allow us to tell the difference between these two sets of spectra. For instance, if we take a lump of any old piece of metal, then a cubic centimeter of metal will contain that many atoms. Huge number, 10 to the power 23 atoms in 1 cubic centimeter of stuff. Doesn't really make a lot of difference which metal we choose. If we were to ask, what about the Earth's atmosphere? Well, you might be surprised to know it's a huge number of atoms. It's much smaller than the number in a solid, but if you think about it, you know, when you're walking through air, you're just pushing these atoms or molecules aside. There's actually a huge number of them in each and every cubic centimeter of the Earth's atmosphere. What I'm sure you'll find surprising is the fact that when we look at the sun's surface, the number of atoms per cubic centimeter is actually lower than the number of atoms in the atmosphere in which you're currently sitting. When we go to the outer part of the sun's atmosphere, it drops dramatically. And now we've only got millions of atoms in a cubic centimetre, not millions of millions of millions. And if we think about a nebula, it's dropped again. We only have thousands or so of atoms in a cubic centimetre of a nebula. If we were to go halfway between here and the nearest star, we would have something like 1 atom per cubic centimetre. If we were to go halfway from here to the Andromeda galaxy into intergalactic space, the number of atoms we would expect in a cubic centimetre, not strictly 0, but if we were to pick a random cubic centimetre, we wouldn't expect to find an atom in there. There might be 1 atom per cubic metre. So the chance of finding one in a cubic centimetre would be very small. So from these numbers, we can sort of deduce that, well, for the top 3, there are so many atoms in a cubic centimetre, they're always going to be bumping into each other, which is why those objects produce effectively continuous spectra. The star produces a continuous spectrum from red to violet. And similarly, if we were to heat the Earth's atmosphere up or measure it in infrared, again, we would find a complete spectrum. However, when the density gets very low, that's when we would expect to get atomic type spectra, spectra that just reveal the particular colors corresponding to the atoms in the medium. So that's why when we try and photograph a nebula, we might choose to photograph only at specific wavelengths because that's the only wavelengths that the nebula will be emitting, corresponding to hydrogen or oxygen or whatever other elements are present. That doesn't mean to say that we shouldn't do the same with the sun. The sun emits across all colors, and we can still choose, if we wish, to image the sun either in white light, all wavelengths, or we can choose to look at it only in hydrogen light at the red end of the spectrum, or we can choose to look at it in calcium light at the other end of the spectrum. Each of these wavelengths gives us information about what particular atoms are doing on the sun, and that gives us information about certain structures around the surface of the sun. So let me wrap up in the next 5 minutes, 10 minutes or so by thinking about spectroscopy. We thought about the colors that stars produce, the colors that nebula produce, but there are other things we can do with the colors of light. For instance, this little animation here is thinking about an exoplanet going around a distant star, as seen from above in the top left of the diagram, and as seen from the side in the bottom left of the diagram. So the motion of the exoplanet around the star is making the star wobble. So for some of its time, the star is moving towards us, and for some of its time, the star is moving away from us because of the influence of the exoplanet. And that's indicated by the diagram on the top right. The speed of the sun, the star, relative to us is positive or negative, depending on whether it's moving away from us or moving towards us. And hence the speed, it might only be literally a few meters per second, goes from 0 to a positive number to 0 to a negative number. And that corresponds to, if we were to look at the spectrum, we would see, for instance, spectral lines shifting towards the red, shifting towards the blue, shifting towards the red, shifting towards the blue. The longer we watch this star, the easier it is to recognize that the various spectral lines are moving. And if we watch it for a number of years, years in the sense of the planet going around the star, then we can monitor how much those lines move and deduce how much the star is wobbling and deduce the existence of the exoplanet. So many, many exoplanets have been found by looking at stars and looking to see if the spectral lines go back and forth, indicating what we call a Doppler shift. It's the same shift that you would hear if an ambulance siren goes past you. As it approaches you, it appears to be a very high-pitched sound. As it moves away from you, a rather low-pitched sound. So we can use the light from a distant star broken into its colors to actually tell us not necessarily anything about the star per se, but about the planetary system around that star. We can also take into account the fact that the universe appears to be expanding, and therefore light from very distant objects gets stretched by the expansion of the universe, and we can use that to get a measure of how far away objects are. We use the symbol Z for the redshift, telling us how much has the light stretched compared to how long it was in the first place. In other words, if the wavelength doubles, it's got stretched by the same amount of its original wavelength, and we call that a Z of 1. And just for a sort of yardstick, a redshift of 1, meaning the wavelength has effectively doubled from this object moving towards us through an expanding universe, that corresponds to the object being some 10 billion light years away. It's a very useful yardstick at very great distances. And a few years back during lockdown, I told you about this particular quasar that you can see indicated by the red lines there, a very distant object about 25 billion light years away. I've gone back to that since 2020 and reprocessed it in color to see if I can bring out any color. And it's not as good and it's more noisy on the right-hand side, but I hope you can see that this object actually looks rather red. One of the reasons I showed you it in monochrome back in 2020 was because it looked a little bit noisy when I looked at the color image. But now I think it's actually quite interesting to look at the color image, and this might not show too well, but I hope you can see that if I split it into the red and the green and the blue part of this color image, the object shows up as a dot in the red part of the channel. The green, you might not see anything. It's just about there, but the green is very faint. And in the blue, there is absolutely nothing that I can see above the noise level. So this object is quite definitely very red, because I can see it in the red, I can hardly see it in the green, and it's not there in the blue. Why am I telling you about taking a picture of an object and breaking it down into 3 separate colors? That's because what big telescopes do as well. The James Webb Space Telescope spent some of its time in its early months looking at various objects in deep fields such as that. And I'm not sure you can see the detail, but if we just look at the bottom one, for instance, it's found a particular object, and rather than taking a spectrum, which would tell you how far that object is away, if you take the spectrum, you can get the redshift, you know how far away that object is. But that's difficult. The first thing they did was take a picture at long wavelengths and take a picture at slightly shorter wave, and take another picture and another picture and another picture, a little bit like my 3 red, green, blue. Long wavelength, middle wavelength, short wavelength. That's precisely what the James Webb was doing in its early months. And it found various galaxies which they said look very bright in the long wavelengths, but I can hardly see them in the short wavelengths, just like the quasar I showed a moment ago. And so the deduction is, the inference is, this object shows up in the long wavelengths but not the short wavelengths. This must be quite redshifted. This is probably a very distant galaxy. Unfortunately, the media picked up on this and said, the universe is broken, because the James Webb has found very distant galaxies which shouldn't be there. They shouldn't be there at that enormous distance. And when the people who took this data went back to this particular object and eventually had enough time to take the redshift to make a spectrum, which takes longer, and find out what the actual redshift was, it turns out that galaxy was a lot closer than they first thought. In other words, measuring the distance by taking a picture at this wavelength and a picture at that wavelength and a picture at that wavelength, it's a fairly fast thing to do, but arguably it's a fairly crude thing to do. It's called photometric redshift. It's not taking a spectrum and looking at what the spectrum looks like. It's taking a few snapshots at different wavelengths and making a guess. And unfortunately, the guess was, this appears to be quite distant. Turns out they were wrong, but that doesn't stop the sensationalist headlines grabbing hold of it and saying James Webb has shown that the universe is broken because apparently galaxies existed too soon in the early universe. So that's just a reminder that a lot of data doesn't necessarily come from true redshift. It comes from a sort of proxy for redshift, which gives us an idea of the distance. But in this case, perhaps it wasn't looking red because it's a really distant redshifted galaxy. It looks red because it's a red galaxy. It's nothing to do with the redshift, or it could be to do with the redshift, but it's not just because of the redshift. It might be that this galaxy happens to contain an awful lot of red stars, maybe. The point is, be careful with interpreting early data that comes out as provisional. The scientists said this is a candidate for a very distant galaxy, but unfortunately the candidate for sometimes gets lost when you read headlines on web pages. Let me just finish, because I'm sort of done time now. Let me just think about beyond colour, a question which I'm sure a lot of you get when talking to other people. Does the Hubble Space Telescope give you actual true colours? When I look at the pillars of creation, is that what the pillars of creation actually look like if I were to go there and stand in front of them? If they were bright enough, if my colour vision worked, is that what they would look like? And the answer is usually no. Occasionally, the Hubble produces true colour images. But generally speaking, the answer is no. It doesn't use a red filter, a green filter, and a blue filter to generate a red, green, blue montage, which then produces a colour image. It takes 3 images at 3 different wavelengths chosen for their scientific meaning, not because it happens to be red, green, and blue. So in this particular case, they figured that the pillars of creation in the Eagle Nebula M16 probably contained a lot of hydrogen, a lot of oxygen, and a lot of sulfur. That's a lot of different elements. A lot of different nebulae have that particular combination of elements. So they've taken sulfur and hydrogen and oxygen images, and then they have arbitrarily said, I am going to make the sulfur image the red channel, I'm going to make the hydrogen the green, and the oxygen the blue. In 2 cases, that makes sense, because sulfur is in the red and oxygen is in the sort of bluey green. But of course, you can see that hydrogen, which glows in the red, has actually been assigned to the green channel. So no, it would not look like this, because the colors are artificial. Now, to their credit, virtually everybody in the Hubble program and elsewhere try, wherever possible, if they've chosen 3 wavelengths and then map them onto red, green, blue, they try and keep them in order. These lines don't cross. The long wavelengths are assigned to red. The short wavelengths are assigned to blue. The middle wavelength is assigned to green. They don't swap things over, so at least you know the ordering is still the same. But you can't say that the color you end up with is in any way natural or in any way true color. So this is the so-called Hubble palette. Some amateurs have chosen to use this same palette. If they take images at these 3 wavelengths, they will color them the same way in order to give images which look like they were taken with the Hubble Space Telescope. Now, of course, this applies to the Hubble in the visible part of the spectrum, but there's no reason why you don't do the same thing for any wavelengths. You're not limited to just assigning red, green, and blue to 3 wavelengths that happen to fit in the visible part of the spectrum with colors that we recognize. You could do exactly the same thing, for instance, in the infrared. And of course, the James Webb Space Telescope never produces true color images because it's working in the infrared. And we wouldn't see anything if they produced images in the infrared. So they have to take 3 wavelengths and say this wavelength is going to be mapped to the red, this wavelength is going to be mapped to green, this wavelength is going to be mapped to blue. This shows you the complexity of a JWST filter wheel. It's got more than one, so it's got at least 24 different filters that it could use to filter light across the infrared part of the spectrum. And it will then construct an image. For instance, this one that I've shown before last year. This is the Tarantula Nebula. A lot of the center of the Tarantula Nebula looks quite white. That's because they have mapped the red and the green and the blue to 3 particular wavelengths, chosen not because of aesthetics, but chosen because of the scientific information it gleans. By taking this wavelength, they see where the hydrogen is. By taking this wavelength, they see where molecular hydrogen is rather than atomic hydrogen. By choosing this wavelength, they get an idea of where the dust is. And hence they can deduce what's going on around this star, because it matters whether the hydrogen is atomic or molecular. Are they bonded together or are they free-floating atoms? That makes a difference to how stars form. And this was an observation of the Tarantula Nebula specifically to try and get a better understanding of star formation. So the image produced is red, green, and blue, but that bears no relationship whatsoever to the red, green, blue colors. They are just colors chosen so that humans can see the final image. If you ever go to the James Webb Archive and download a picture like this, you might say to yourself, that looks very nice, but I wonder what the colors mean. Well, there's what the colors mean. They're always on these images if you get them directly from the web pages. They tell you that the blue was this filter, the green was this filter, and the red was this filter, and they give you the numbers. They tell you what the actual wavelengths were, and the little letters on the end tell you whether it was a narrowband filter or a wideband filter. Most people don't care, but if you are interested, the information is imprinted on the bottom of all of these so-called compass images that the James Webb Space Telescope produce. So most amateurs doing astrophotography choose to take pictures in natural light, in other words, true colors, and some amateurs will choose to use false color like the Hubble palette. The professionals will almost universally use false color if it gives us more information about the object we're trying to image. If aesthetically it looks better in true color, they'll produce an image in true color. But most of what professional telescopes are doing is trying to extract information from these objects rather than trying to produce pretty pictures. So let me summarize by recounting most important points of what I've said. The most important thing is that the eye is not a camera. The eye is a much more sophisticated device. It does not simply record light intensities in the red and the green and the blue part of the spectrum, feed that information in the brain, and then let the brain take care of forming an image. Much more processing is done in your eyes than you realize. And that's why we got those rather odd results of the blue and the yellow tiles early on in the lecture. The colors of stars are determined by their temperature. If you take an object and heat it up, the amount that you heat it up will determine the light that comes off. That will determine what it appears to look like. And the light from stars will be either reddish or strongly red or white or blue. But it will not be purple, it will not be green for the reasons I showed earlier. If we're looking at nebulae, because the atoms are so far apart, they're not rubbing shoulders with each other, we're getting the pure spectra from the atoms, not blurred spectra, if you want to think of them that way. And so the spectra we get from nebulae are telling us about the individual atoms, the individual constituents of those nebulae. And if we break the light from distant objects down into the spectra and examine it very closely, by looking at how lines are moving, we can tell whether or not those stars have got distant exoplanets. We can not only tell about atomic composition, which is what I mentioned here, we can get velocities because of the Doppler shift, and because the universe is expanding, we can also use the colors of objects to get distances, as long as we're careful about how we interpret this object looks red. Does that mean it's very distant, or does it just mean it looks rather red? So we do have to be careful. But if any one of those take-home messages are taken home, then I think you've understood just a little more about the nature of color in the cosmos. Thank you all very much.